All right, welcome. Today we are going to tear down the blueprint of a major energy project. And our goal? To find every single opportunity for improvement. We're talking cost optimization, efficiency gains, everything we need to learn how to turn a good project into a truly great one. Think of this as your practical guide to finding that hidden value in every single design decision. Let's get right into it. So this is the big question, isn't it? For every developer, engineer, and investor out there. Look, it's not just about getting a project built. It's about building it smarter. And this isn't just theory. We're going to get into the practical, on-the-ground decisions and trade-offs that unlock that hidden value, that boost productivity, and really, that strengthen your bottom line right from day one. So, here's our game plan. First, we'll tackle what I call the project puzzle. Then we'll dive deep into choosing your core technology and designing smarter systems. After that, we'll look at optimizing for the long term, and finally, tie it all back to the real-world value that all these improvements actually create. You know, every large-scale energy project is like this incredibly intricate puzzle. You're juggling land use, technology, connecting to the grid, financial returns. It's a lot. But right there, inside all that complexity, lies just enormous potential, and it's just waiting to be unlocked by intelligent design. To really get a handle on what's at stake, let's look at a real-world example. What you're seeing here is the total installed energy capacity in a huge, fast-growing economy like India. Now, that renewable slice, your wind and solar, it's already massive, and it's growing like crazy. In a market this big, think about it. Even a tiny fractional improvement in efficiency translates into absolutely massive gains in energy and, of course, revenue. And the potential, it's just staggering. I mean, look at this number. Nearly 700 gigawatts. That's the estimated untapped wind power potential in India alone at a modern turbine height. The only way we're going to harness this effectively and economically is through superior project design. That's the gap we're here to close.
So here's the crucial point. A successful project isn't just about maximizing one single thing. It's a really delicate balancing act. Are you trying to squeeze every last kilowatt hour out of every square meter? Or is your main goal to get the lowest possible levelized cost of energy, the LCOE, which is basically the lifetime cost of your electricity? Maybe you need super stable power to match what the grid needs. These goals, they often compete with each other, and your design choices have to navigate all of these trade-offs.
Okay, so that brings us to our first set of really critical decisions, the hardware. The technology you pick lays the foundation for your project's performance for the next 25+ years. Getting this right, it's absolutely non-negotiable. A perfect example of this is just how solar panels have evolved. I mean, we've moved way beyond the standard panels to what we call bifacial modules, and these things are total game changers. They're double-sided, so they capture light from the front like a normal panel, but, and this is the cool part, they also capture light that reflects off the ground onto their backside. Now, what I love about this slide is how it really visualizes that extra energy gain. You've got the direct sunlight, sure, but then you also see the diffused light from the sky and, critically, the ground albedo. That's just the light bouncing off the surface below. By capturing all that reflected energy, these bifacial panels can boost generation by up to 20%, maybe even more. It all depends on the ground surface. That's a huge efficiency gain from just one technology choice. But of course, it's never just one option, is it? This table really breaks down the classic trade-offs. Here's a simple way to think about it. If your project is tight on space, then maximizing every kilowatt hour per square meter is everything. That makes high-efficiency tech like bifacial really attractive. But if you've got plenty of land and your main driver is keeping those upfront costs down, well, then the most cost-effective module might be the smarter financial play, even if it's a little less efficient. It always comes back to your primary project goal. And this brilliantly illustrates another fundamental choice: how you're going to convert that DC power from your panels into grid-ready AC power. Over on the left, you've got the central inverter model. Think of it as one big centralized brain for a huge block of panels. On the right, you have the string inverter model, a more distributed approach with lots of smaller brains, each one managing a small string of panels. Now, this choice has massive implications. Central inverters, they usually have a lower upfront cost per watt, which looks great for these big, uniform solar farms. But they're a single point of failure. If that one unit goes down, you lose a massive chunk of your power. String inverters, on the other hand, cost more upfront, but they give you so much more resilience and flexibility. If one fails, you only lose a tiny piece of your plant's output. This is a classic risk versus cost decision you have to make right at the design stage. Okay, so we've talked about picking the components. Now let's talk about how we arrange them. This is where really clever system design can just multiply the value of your technology choices.
For wind farms, one of the most powerful tools in your arsenal is something called microsighting. Think of it like playing players on a soccer field. You don't just throw them out there randomly, right? You position them strategically so they don't get in each other's way. For wind turbines, this means minimizing wake effects. That's the turbulent, low-energy air that one turbine creates, which can kill the efficiency and ramp up the stress on the turbines behind it.
And this is all guided by some pretty detailed analysis. This slide shows a common rule of thumb, spacing turbines about 5 times their rotor diameter apart in the direction the wind usually blows, and 3 diameters apart perpendicular to it. Seemingly small tweaks to this layout, based on complex modeling of your specific site, can dramatically increase the energy output of the entire farm over its 25-year life. It's huge.
Now for solar, there's a similar layout decision. Do you keep your panels still, or do you have them follow the sun? A fixed tilt system is simple, it's cheap, it's reliable. A single-axis tracking system, though, is more expensive and more complex, but as you can see, it can generate 10 to 25% more electricity just by following the sun across the sky. So again, it's a trade-off. The calculation is simple. Does the financial value of that extra 25% of energy over the project's life outweigh the higher upfront cost and the long-term maintenance of the tracking system?
So here's the thing. These design decisions, they don't just affect your construction costs or how the plant performs on day one. No, they have consequences that ripple across the entire 2-decade-plus life of the project, especially when it comes to just keeping the thing running smoothly.
These right here, these are the core goals for any operations and maintenance team, any O&M team, and a smart design is their single greatest ally. Choosing string inverters, that directly minimizes downtime. A thoughtful micro-siting layout that reduces wear and tear on your turbines, extending their lifespan. Even something as simple as designing wider access roads for cleaning crews directly maximizes production because it makes cleaning faster. Seriously, thinking about the person who has to maintain the plant in year 15 is one of the highest value things you can do in year 1.
Okay, let's pull all these threads together and talk about the ultimate metric, value. How do all these technical decisions actually translate into better financial outcomes for everyone involved?
You know, this quote just perfectly captures what we've been talking about. It's not about having the flashiest, most expensive equipment. It's about the intelligence you apply in picking it and arranging it. Every single decision, from choosing a bifacial panel to adding an extra meter between turbines, is an investment. Smart design is what makes sure that investment gives you the highest possible return by cutting costs, boosting revenues, and lowering your risk over the long haul. So here's your checklist for finding that hidden value. 1. Start with your main goal. Lowest cost, highest density, whatever it is, and let that guide every tech choice. 2. Model the trade-offs. Don't just guess if a tracker is worth it, calculate the lifetime value of that extra energy. 3. Remember that small optimizations compound into huge returns over 25 years. 4. Design for the person who will be operating and maintaining the plant. And finally, just make this kind of critical analysis a standard part of your process.
And that leaves us with one final question to think about. The value, it's always there. It's hidden in the trade-offs between different PV modules, in the spacing of wind turbines, or in the choice of an inverter. The challenge, and really the opportunity, is to apply this kind of critical thinking to find it. Thanks for tuning in.